All right. So these are us, Nathan, Dan, Matt. You don't have to remember that. You can be like bald guy, whatever, guy in the hoodie. That all works. All right. So let's kind of jump into it. So synthetic data. Well, first of all, how many people here are sort of familiar with synthetic data conceptually? Yeah. So this is not news to you guys, and I don't want to spend too much time on this, but how many of you, if I say physics-based synthetic data as opposed to generative, sort of have a sense of what that means? All right, cool. A little bit less. So let's spend some time on the types of problems that we're trying to solve, and then that'll make, will make more sense as we get into how we solve them. So the types of things that we're addressing with synthetic data sort of start with rare events and edge cases. It's a common use case for synthetic data. So this is, especially as you start to deploy computer vision models, what's often found is that the really high AP score that you got suddenly doesn't matter so much because it's breaking on things that it just doesn't seem very often. And so I like to joke sometimes that artificial intelligence is not the first form of software that doesn't have bugs. And rare events and edge cases tend to make up the types of bugs that we find. So there's these circumstances where we haven't seen something very often, or haven't seen it at all. It's rare. And so we need to create those examples on a training set in order to actually address that. So we need to be able to show our system what types of things it should be finding. Another major issue that we find repeatedly is that when you move out of RGB imagery, so if you move out of sort of standard cameras and into things that are industrially important, so that can be infrared imagery, radar imagery, hyperspectral imagery, it becomes much harder to label that data. So you can no longer just sort of take it to SageMaker ground truth and have people label that. And in fact, it's often hard to even know what's in some of those images. So like, for instance, radar imagery, unless you have a priori knowledge of what was being sensed, your eyeballs can't detect what's going on. But the third reason, and this is one that I think really was the reason that we founded Rendered AI in the first place, is that if you stop and think about the types of problems we're addressing with computer vision today, they are almost entirely predicated on sensors that were designed without AI in mind. So they're cameras from our cell phones and things that were meant for human eyeballs to look at. And now we're trying to use artificial intelligence to look at them instead. And so what happens is, as you think about what you want to design for your next generation system, you have this gap because you need to design it before you can build it. You need to build it before you collect data. And now I need to collect data before I know what it is that I actually wanted in the first place. And I personally saw that happening a lot in the satellite industry. Oh, that's fun. Okay, it's falling asleep. So we just need to remember to. Okay. So my background actually was in satellite communications before founding Rendered AI. And so in the satellite industry, I regularly saw this problem with companies where really brilliant engineers would have some cool sensing technology. And we would talk about how they could bring that to market. And they would say, okay, nobody buys imagery, they need insights from the imagery, which I think is probably a common problem to what you guys are dealing with. I don't just want pictures, I want to know what's in the pictures. And in order to do that, we're going to use AI. And you go, great, how are you going to do that? And they say, well, here's the plan. We're going to raise $200 million. We're going to build satellites for 2 to 3 years. We're going to launch them into space. We're going to collect data for 6 months. We're going to label the data for another 3 months. We're going to build an AI system on the back of that data, and then we'll figure out whether we can create value for anybody. Right? Doesn't work. And so that creates, I mean, and if you stop and think about it, right, that's a pretty significant barrier to what our next generation systems really should look like. And physics-based synthetic data and synthetic data broadly is a way for us to address that. It's a way for us to bring, if you're in other forms of engineering, you might hear people talk about model-based design or model-based engineering. So synthetic data is a way for us to bring model-based engineering into the world of computer vision. And then finally, and we won't talk about this too much today, but you can use synthetic data for things like anonymization and privacy, and that is important in some circumstances. And that's also a place where generative AI can be particularly useful. But I also like to show this because I think it's relevant. I think it's relevant to the engineering community around computer vision to think about the types of workflows that we actually are using. And by the way, for those of you taking pictures, you're of course more than welcome to take pictures, but if you'd like the slides, we can also just provide you with the slides afterwards. So don't feel like you have to take pictures in order to have access to this content. So in a conventional computer vision model engineering practice, you sort of start with a data set. And I guess, you know, most of you, if not all of you, have trained computer vision models at some point. So how many of you typically sort of are handed a data set at the beginning of that process? Not many. Okay, how many of you had to go get a data set in the first place? Weren't even handed a data set? All right, even more. All right. So usually, like, best case scenario is you're given a data set, and that's sort of a static asset that you start with, and you begin training a model. You know, pick an architecture, start tuning hyperparameters, train, iterate, you know, and then eventually you get to a place where you accept or reject the result. And reject usually means we don't have the right data, right? We have to go back and collect new data, which can be expensive and time consuming. And what we think,
I don't think you're sharing it.
I'm not sharing my screen again. Just let me know as that happens if that doesn't.
Yeah.
Okay. What synthetic data offers the promise of is being able to actually bring the data into that engineering effort. So now actually incorporating not just a replacement data set, right? Not just, hey, I had real data, maybe I can get a synthetic data set faster or cheaper, but I can actually iterate on that synthetic data set. I can address bugs as they come up. That becomes a part of the engineering loop.
So I think you need to share it on Zoom. Like share your
Oh, that would make sense. Sorry, guys, one moment. Share all of this stuff too. Okay, that should do it.
Yes.
All right. Does every so just to check in again, presumably if you're here, you're interested in synthetic data other than him. Does it make sense like why you would care about synthetic data? Is everybody's on the same page? Okay, so at this point in the talk, we're going to assume you think synthetic data is cool. You've selected several things that suggest that might be the case by being here and by staying with us. So we're not going to talk about that anymore. We're not going to talk about why synthetic data is cool. What we're going to start really moving into is how do you actually go about generating synthetic data and getting into like the mechanics of it. So what is actually required to generate data and also to be successful with that data. And what we find is that when most people begin that journey, they start with a simulator in mind. So they say, I need synthetic data, so therefore I'll get Unity or Unreal or Blender or some other type of physics simulator. And if it's a really high fidelity physics simulator, then that will mean I get a good data set because I'm calculating the physics properly. And that will mean that I get a good AI model. And it turns out like there's some truth to that. You do need, wow, this is terrible. You do need a good physics simulator. But it misses a lot of the really important parts of building up effective synthetic data. So for instance, what are you simulating? Right? You need to be able to generate environments.
Stop sharing.
It's not reliable hardware. Let me try this.
Also, can you check if there's anyone in the waiting room? I don't think I can control that.
Yeah, there are a few. Oh, this will be fun, guys. We get to work through technical challenges as we go. It'll be a good time. All right. So if you assume that it's just a physics simulation, and that's all that you need, you miss out on some really important things. You miss out on how you generate the environments that you're going to simulate in the first place, whether that be 3D modeling, procedural generation, generative techniques for things like textures or again 3D models. So all of that world building has to happen somehow. Usually in the work that we do, that's then getting pipelined to some form of an HPC environment, usually in the cloud. So there's a whole other set of engineering required to make sure that that happens at scale and at speed, because this is not something you do once, but something you actually iterate on. From there,
Are you actually sharing?
Yeah.
Showing up.
Um, is it back?
No. This is sort of the screen sharing.
How about now?
Yes.
All right, I have a feeling we're gonna have to keep doing that. Okay, so now you've pipelined things to the cloud. Yeah. Now, as a data scientist, you have access to data, but maybe an obvious question, is it any good? Right? What's the quality of that? Does it match the domain? Do I have to do domain adaptation? Are there other post-processing techniques that have to be integrated? And then, and this is, very broad, but how do I pipeline that into an MLOps framework? How do I actually run experiments? How do I do all this quickly enough that I'm not spending months trying to iterate, but it becomes something that we can cycle through, testing quality, iterating, having data provenance and history? All of this requires tooling. And not only does it require tools, but really, if you stop and think about it, if you were starting from scratch, there's several different types of skill sets involved. So getting people that have 3D modeling and simulation experience pipelined into people that have cloud engineering experience and data scientists means that you've got all of these different groups that are now participating together. And for most organizations, that's more than they're really able to pull together. There's it's expensive talent. And the Venn diagram of overlap in these types of capabilities is pretty limited. So most computer vision engineers don't come with great depth in 3D modeling and simulation, and vice versa. Cloud engineering is, of course, its own art. And so it's helpful to have a platform that brings these tools together. And that's what we're doing, and that's what we'll be talking about today. So we'll be talking about how does that really happen? What tools are they? And in particular, those two personas, the synthetic data engineer who's dealing with things like 3D modeling and simulation, and a computer vision user that needs to be able to task a system to actually get data, assess quality, and pipeline that over to MLOps. How do they interact? Like, how do they actually work together to get these jobs done? That's what the platform is designed to do. And yeah, so we'll be able to walk through a good chunk of that today. But before going too far, because it's so hot, and I think a lot of people are thinking about it right now, it's helpful to spend just a little bit of time thinking about what's the distinction between physics-based simulation and generative AI as a way to generate imagery. Because I think probably a lot of you, if you're thinking about synthetic data, are thinking about, like, when do I use which and why, and what should that mean? So I'm going to spend just a little bit of time on that first. And I actually, this is based on a talk that I gave at an earlier conference, where I don't think that it's an either or choice. I think actually that both are really important. You get new types of information from both. And increasingly what we're seeing is that data moves in and out of generative techniques and physics-based techniques. And I'll share a little bit about what that means. I'm going to keep going here. So there's a famous physicist by the name of Ernest Rutherford who quipped about 100 years ago that all science is either physics or stamp collecting. He had really high opinions of people in biology and chemistry. And of course, he was sort of, at the time, what it meant to do biology was you went out and you found species and you labeled them. And that was what it meant to do that. But I feel like, the joke's on us as physicists, because now it becomes, well, what if I had 100 billion stamps? Turns out you can do some pretty interesting things. And these are really two different ways to understand information. So here's a $100 question for you. How many of you heard the word epistemological before? All right, epistemology is the study of knowledge. Okay. And these are two different ways to define knowledge. One is to have a set of equations that help us predict things. And another is literally to just to list things out in a library. And they're both relevant and they're both important, but they do different things for us. And in particular, the use of all those stamps help us do really important things even after physics-based simulation. In fact, one of the ones that we'll talk about as we do our demo is just domain adaptation, where we use our physics-based knowledge first, but then apply this generative techniques to be able to better match what came out of the simulator to the domain of a real-world sensor. And increasingly, what we're finding is that we'll continue to move in between these sort of, let's call them generative techniques and rule-based techniques, where we can use generative techniques to define behaviors, to actually create prompts. We can use generative techniques to do things like 3D model generation. But then when it comes to specific models, or if you're trying to detect specific behaviors, you often don't want to use generative techniques because you want to make sure that you're really specific about what's being implemented. Things like agent factories, motion and interactive motion tend to work better with rule-based techniques. But surface textures and the way that we paint things, generative works great. And then, of course, simulating sensors themselves tend to work best with rules-based, because you actually can get into what's happening with the photons usually, or whatever the imaging-based medium is. And so we are talking about a platform for physics-based synthetic data generation. What we mean when we say that is there's always some form of physics-based solver behind the scenes, but that's not to the exclusion of generative techniques. In fact, a lot of what we do involves both. But we get new information from the physics-based solver. So we don't rely, and in everything that we're showing, we're not relying on the existence of a data set a priori. So, and in particular, the types of problems we're trying to solve, like rare events and edge cases, cold start problems, and areas where data labeling is incredibly difficult, those are all really hard to do if you require a labeled data set to get started. All right. The other thing I want to touch on before we get into sort of applications and kind of hand it off is what synthetic data looks like in practice. So in a commercial organization, what does it really look like? And it's easy to say like, oh, well, that's fine. We have a synthetic data app of some kind, and somebody sits at the app and they press a button and they get synthetic data out, right? But usually that's not the case. Almost always it's collaborative. And almost always, in fact, it's collaborative across multiple organizations in our experience. So you end up with people in either different departments within an organization. That can be the sales team is interacting with the engineering team, management, et cetera, or actually different organizations. In this case, we're looking at a specific example in remote sensing where Orbital Insight partners with folks like Booz Allen and Deloitte to solve problems for their customers. So you need some place that you can actually work together collaboratively. And furthermore, not everybody actually access these things through a web-based browser, right? So you also need to be able to access that through APIs and SDKs that can be pipelined into other interfaces for synthetic data. In the case of remote sensing, there's tools like ArcGIS that are regularly used to do the follow-on analysis. So like somebody's collecting imagery, they're trying to analyze it. There are tools that are used by that, and synthetic data is a part of those tools, not something completely separate. And furthermore, somebody has to define what's in the sensors, right? So like we talk about cameras as if all cameras are the same. That's not true, especially as you get into industrial applications. So we need input from the people that actually build those sensors, whether they be satellites or security cameras or X-ray systems. Furthermore, we need to be able to integrate differentiated types of simulation. There is no single simulator out there to rule them all. I think Omniverse wants to do that. I'm pretty sure Unreal wants to do that too. The reality is there are a lot of different types of simulation and simulation tools out there. And to be an effective tool, we need to be able to integrate that community. And then finally, you have systems integrators that actually put these things together. So you know, in the real world, these systems are complex. It's not just a sensor provider sort of delivering a whole value proposition. It's usually that's being brought in along with other data sources to build up a view and analytics. That work is being done by systems integrators. And then even that then needs to feed more people. So one of the really interesting, we have a customer who started using synthetic data for their engineering team. They were designing the next generation platform. They wanted to start training models ahead of time. And then as soon as it spun up, who became the biggest users? Their business development team, because the business development team needed to show their customers what was possible. And this is an example of like synthetic data. It doesn't end with just creating improved CV models, but there's a whole community of people that end up participating in this process. And I'm going to stop here, but I just want to share, when we think about synthetic data and what it really means, it's about creating the space for these different organizations to actually work together and share information in the world of artificial intelligence. And so it's we take a fairly expansive view. Now, I'm going to just run through a few applications so that we can kind of talk about where the rubber meets the road a little bit, and then we're going to get into stuff that you can do immediately. But I want to share some of the things that we've been up to at Rendered. So we do a lot in satellite imagery and remote sensing. These are examples of kind of city building and RGB sensing from space. We do this is called synthetic aperture radar. I'm actually curious, for those people in the audience, how many of you heard the term synthetic aperture radar before? All right, quite a few. So if you want to do imaging through clouds, through rain, this is a way to do that, where you actually take not a radar image, but you take tens of thousands of radar images and then post-process them to be able to generate an image. And actually what we're showing here is a video of a tanker ship as it rotates, showing how different it can actually look based on the position of the ship relative to the sensor. We do hyperspectral work on our platform. So hyperspectral tends to mean so RGB, you're all familiar with, that's 3 bands. Multispectral or infrared sometimes will have like 5 bands. Hyperspectral usually means hundreds of bands or thousands of bands. So you're really starting to break down and be able to look at in minute detail what's happening spectrally. This becomes really important for things like monitoring crops, for methane detection. In fact, what's showing here is actually a plume simulation, methane plume simulations. This is work that we're doing with Planet, one of the world's largest satellite operators. So just very, very differentiated physics. And again, something would be hard to just like label. If you just go out and collect hyperspectral data, it's hard to know exactly where the methane plumes are, for instance. It's also useful, and people use this for multi-sensor domains. So here we're showing a mid-wave infrared sensor as well as RGB co-located. We've gotten into a number of different healthcare applications. In this case, this is showing a microscopy video of an oocyte, which is part of an IVF application trying to detect oocyte morphologies and understand the health of embryos. X-ray, this is actually one of my favorite projects. We're actually working with a company to help detect weapons that would otherwise enter schools. So actually, this is part of a rapid X-ray scanning system. And this is a classic systems engineering question, right? How fast can we move things through this system and still keep our children safe? It's an important problem, right? And then there's a lot of knobs on an X-ray system. Like what if we change the voltage? What if we change the resolution? The faster we can go and the cheaper we can make it, the better. We're working with one company on eliminating or trying to eliminate racial bias from consumer-facing applications. So in this case, actually detecting eczema on skin and giving them tools to introduce basically additional racial characteristics into their data sets. We're working with a large rail company on identifying defects that would otherwise lead to train derailment. I don't know if you guys can see it. There's like a little crack in that wheel. So this is an example of a fully synthetic image with a procedurally generated crack. And then the last one I'll show, just insurance company in this case, wanting to be able to detect different parts of a house and identify when damage is present. So this is not exhaustive of the types of content on our platform, but I wanted to give you a flavor of the breadth. So this isn't, it's not all social media images. I actually didn't show any autonomous vehicle work. My apologies if those of you who might be interested in autonomous vehicle work, but we do a lot of differentiated things. I personally feel like a lot of these are important problems to address. Like these are a lot of these are pretty crunchy computer vision applications that have a real world impact. And so we're excited to be there. All right. So we have reached the first break. We were going to take a 5-minute break, let people use the restroom and things. But before we do that, does anybody have any questions on the platform, what we're doing, kind of the approach? The rest of the presentation is going to assume that you kind of understand our intent. So yeah.
A couple of times throughout the presentation, you mentioned edge cases and outliers. Are you guys doing any generation for those use cases? And if so, have you guys noticed any difference in accuracy when doing using generated models versus physics-based simulators? Is one better than the other?
It's a good question. So we do a lot of work on rare objects and edge cases. That's the majority of our work is in that space. We don't do pure generative, so I don't have an A/B comparison with pure generative, but we work with a number of different organizations who have, and they'll come to us often after they've tried that. So they'll start with pure generative. They're not, there's issues with sort of model collapse or just not having, anything in pure generative is still based on data that exists at some level. And so they'll come to us afterwards. And we've had a lot of success in those circumstances, although sometimes not in full transparency, sometimes not as a drop-in replacement for the real data set. So the things that work really well, we found, especially when they're, let's say, just really difficult sensing applications, small number of pixels, low signal to noise environment. Some of the things that work really well are bootstrapping using synthetic data, where maybe you have data set, but you've got a billion images and you can't label them all. And so what you need to do is cut 3 or 4 nines out of that in order to find your rare edge cases. The second is pre-training. So we've had a lot of success pre-training on synthetic data, then fine-tuning on a small amount of real data, or fine-tuning on real data that doesn't contain the rare object or rare event. Does that make sense? And so those two things are great ways to sort of use synthetic data in a workflow that gives really successful output. Our experience is actually with the pure zero shot, so synthetic only, you get really, really good recall in most cases. And so what you're fighting is false positives. And so a little bit of real data can help reduce that.
Thank you.
You're welcome. Cool. Are there any, are you guys able to see? It looks like there's some things in the chat. Is anybody having questions in the chat?
Someone had a question about the timetable of this tutorial.
Okay.
So
So hopefully that gives you a sense of the platform. We're going to take 5 minutes. This would be a good time to get your laptops out, because the next thing we're going to do is teach you how to sign up for an account if you want to, and you can generate data in parallel with Dan, who's going to give you guys a demo and tutorial from the computer vision user standpoint. So thanks so much, and we'll start again in just 5 minutes.
now make me a presenter.
I think you have to. I think we might have to restart. You have to go through this process.
I'll need to restart.
Well, let me see if I can from here. Oh, there's more people.
Can't see that. This.
That's a good. Can you make? Yeah. If you can make Dan a presenter, that's one major headache.
I'm going to make you. I can make you host.
Great.
Yeah.
You're the host now. So yeah, now this computer anyway is host.
Yes.
Okay. Do you want to switch? Yeah. Okay. Um. This video is still video. Like I can make you the host, but you're still gonna be Dan Hedges.
Yeah, that's fine.
Okay. I'm sorry.
The video is coming out.
Okay. Hey. Yeah, that's fine. Yeah, perfect. Yeah, that's right. You were in London.
I'm sorry about
Basically,
question.
when I saw that
this
you guys
version
were
of
workshops, so I
some
wanted to
wedding
generate
video
data
videos.
so
Yeah, cool. Yeah, that's the next part. Is it? And in fact, it'll be, we're gonna use geospatial data
That'll be the third,
for the generation.
Second
So-
segment.
yeah, I mean, we were still working through, we didn't feature right now, just because we were working through some internal details. Because I was coming to see if there are that you guys are coming to, like, let me try to do it myself, and then I can ask my team to take it forward.
Perfect, perfect, awesome.
Thanks for organizing this.
We're excited. It's nice to be able to have sort of more expansive time to really talk to people, right? Let's get past the surface level kind of introduction.
Absolutely.
Yeah. Thanks.
One question I wanted to ask you was, no question, but like something that I've been seeing in this conference, visual prompting. I don't know if you had a chance to look into that. Visual prompting was something that at least I attended Andrew's talk, and he basically talked about, because visual prompting has been something where you can interact with like a pre-trained visual transformer model
Mhm.
and sort of start taking like an unlabeled data set completely and just by clicking a few things, it can like auto label some of the stuff.
Yep.
And so I was just curious if that sort of takes through, would that sort of affect headache data? Because like obviously, like in vision, the biggest thing is data and annotation.
Yeah, absolutely. I think something has to jumpstart that process if you're talking about pure cold start. So I actually think if what it sounds like you're describing is a faster labeling approach where you start with pseudo labels and then
The show visual prompting, it was actually pretty cool. No, I'm saying like simulated definitely have its value,
yeah.
but this thing is really starting to come up and a lot of people are starting to talk about it.
Yeah, I'll take a look. Yeah, one of the things we are starting to do is like build those integrations. So like maybe you want to build a visual prompting capability. Start with synthetic data, press a button, get out your visual prompting model or whatever.
Big question.
We've just started those. In fact, we'll try to demo it today, but we have a tool that allows you to spin up ML algorithm, ML training jobs on your own cloud, but from the platform, so you don't have to transfer data. Does that make sense? Yeah, so we're We're working through some of those integrations.
I just wanted to, I saw something cool, so I wanted to share it.
That's awesome. No, I'll take a look. Thank you very much.
Appreciate it. Very nice to meet you.
Nice to meet you.
So we met at G1, so that was.
Oh, yeah.
The other conference or GS.
Yeah, 2 weeks ago. Yeah.
Looking forward to it.
This is the bleeding edge part. I'm here with Travis. And maybe, there, that's definitely changed. It's not shared. There, cool. All right, I think we're ready to reconvene.
Yeah.
Okay, guys, it looks like we're ready to reconvene, so I'm turning it over to my colleague, Dan Hedges, who, you're in excellent hands.
Great. All right, thanks,
you.
Nathan. Hello, everyone. So my name's Dan Hedges, and my section is going to talk a little bit about the synthetic data superpowers that a CV user will have. What sort of powers that synthetic data enables for the CV user, and how using a platform for synthetic data can enable these superpowers. So Nathan talked about it briefly. Let me get this out of the way. There we go. The kind of workflow for what a synthetic data or a CV user is going to do with synthetic data, what those needs are, and we can kind of walk through that here. So first, you want to generate a data set. Likely want to generate multiple data sets and run different kinds of experiments. You then want to build your annotations. So you want to, one of the major benefits of synthetic data is annotations come with it, 100% accurate annotations, but you want to be able to configure that to exactly what your needs are. And then you want to be able to post-process your data set. So we talked a little bit about that domain adaptation and sort of analytics that can be done with that. Then you want to do some quality assessment. Understand how close you are to your real data set and what can be done to bring that closer. You want to be able to then pipeline that into your MLOps framework to be able to get the most out of that data. And then you want to use that iterative process to experiment with new types of synthetic data and understand how those changes that you make impact the overall scores that your model will have. All right, so I'm going to walk through each of these one by one, what these tasks and how using synthetic data with a platform for that usage is going to kind of provide these superpowers. So first off, when you generate a data set, you want to define your experiments. So you want to understand what testing you want to undertake, and you want to be able to then iterate on the types of experiments that you use, what sorts of objects you bring into your data, what sorts of modifiers or environments or different types of blurring or other post-processing effects go into your data, what sorts of impacts those sorts of things have. And so first off, let me go to the browser here, and if you want to follow along and sign up for an account, yep. Oh, is this only?
You want to stop share and then share the whole second. Well, you're on. You got to move it over to the other screen. You
I
want
think I
that to-
shared the whole screen, but let me try that again. You see it now?
You are sharing. You just shared it via Zoom, but that is your second monitor.
This is my second.
Yes, you have to drag the You have to drag that window over and then share your second monitor. Good times. Maybe check the Windows settings and see if you can set it up to use the two monitors as the mirror the two monitors. That looks.
There we go. Okay. Okay, so now you can all see, so to sign up for a free trial of the platform, you can go to render.ai. This is the screen you'll see here. And you can just click this get started link here. And this is gonna just ask you for some demographics, but then once at the end you submit, you will be able to sign into a rendered AI account. So
Maybe just give them a minute for those who want to.
yeah, so if you're doing that on your laptop, you can go ahead and do that now, and we can follow along. So in terms of synthetic data experiments, we had a good kind of example of this recently. So the NSIN, which is the National Security Innovation Network, had a challenge that they put forth to the community regarding synthetic data and the types of experiments and questions that they had regarding what sort of impact synthetic data has on model training and et cetera. So this was the problem statement that they provided. And they wanted to understand three questions. One was, and this was specific for satellite imagery and actually specifically object detection of rooftop AC units, HVAC units within satellite imagery. So they wanted to understand these three questions. One is, how does the inclusion of shadows and varying sun angles affect the optimization of a CV network? Second was, how does the fidelity of a 3D model affect the optimization? And then third was, how does the resolution of your synthetic data affect the optimization? So we felt like that was a really good test case for the rendered platform, because we allow for that sort of rapid experimentation and modification of output data sets. So one of the things that you can do when you sign up for a rendered account, and we'll go into some of the examples of this, but we have various content codes that allow you to quickly get set up with content that we've deployed within that is shareable to all our users. So to do that, I'm going to go here. This is the platform. Once you sign in, you'll see something similar to this. But to do that, we can go into our workspaces pane here, click create a new workspace, give that a name. So I'm going to call this NSIN Gen. That's the name of the competition here. And then to actually activate that content code, you go into the content code section here and just type NSIN -UA. And that's going to set me up with a workspace that contains a variety of different graphs, which I'll show you what those are, and different data sets that have been pre-deployed. So I'm going to jump into this workspace here. So from the organization view, you can see there was a lot of different workspaces. They covered a lot of different content areas. This is an adaptation of our RGB satellite simulation channel. So what that does is it essentially simulates satellite imagery of, with various objects being placed within those satellite imagery environments. So we adapted that to specifically answer this question of what do these certain types of effects or certain types of components of synthetic data, how do those affect the output training of CV models? So I'm going to go into one of these graphs here. So a graph in this case is essentially just a configuration of a simulation pipeline that we have deployed to the platform. So if we zoom in here, zoom in pretty far here, we can see what this entails. So we've got this whole list of nodes, this whole list of nodes that represent various different 3D assets that have been deployed to this channel. So these are all custom built HVAC system 3D models that have been deployed. So we've got, in this case, we've got 3 large systems, 3 medium systems, and 3 small systems. And those are all, and we have a whole bunch more as well. So we've deployed in this case, I think upwards of 20 different HVAC 3D models. But in this case, we've got these 9. And what we're doing with those is we're adding those to this clustering node. So that is going to actually control object placement within the scene. So within here, we can control things like object density, the amount of separation provided between all of these different objects that are being placed, the amount of rotation that we're allowing for and the probability for that. And then that's going into our scene node, and that's going to be combined with a environment. So this background node here, and if we go in here, we can see we have some background nodes as well as some modifiers. So in this case, what is going on with this node is it's choosing from a variety of different existing satellite image backgrounds. So we used the XView data set, which is an open source satellite image data set. And as you can see, we've created what we call agent factories, which are placement areas within these images, as well as added some metadata about things like time of day of the collection and the location. So we can actually simulate objects within those images and accurately and seamlessly represent their shadows and the blur and things like that we go into that satellite image. And then we can also control things like our sensor parameters, that sensor look angle and ground sample distance. So what is the actual pixel size on the ground of the output image? So we can answer that third question about what is the actual effect of having a lower resolution images. How does that impact our model training? But I'm going to go and try to answer that first question. And that was, what does the impact of different shadow angles have on output training? So how if we simulate, like I said, we can simulate the shadow angle to match those input backgrounds, or we can actually have them be intentionally different. And what is the impact of that on our environment here? So if I go into this content pane here, I can click on these modifiers for our backgrounds, and I can go into this random date time modifier. So this is going to allow me to I can quickly add that link between my background and this modifier.
You got it.
Yeah, and then delete this other link. And then add this link in here, and then I can control the start hour. So let's say we want to do 9 a.m. between 9 a.m. and maybe 5 p.m. And it's going to then randomly choose a time between those two, a date and a time between those two times every time it runs. So once I have my graph configured and I want to actually start generating data, I can go to this. I can go to this stage button here, and that's going to take this configuration of my simulation pipeline and stage it for production. So I can go over to my jobs pane here. We can see right away, this is that graph that I had just published or that I just staged. So I can give my data set a name. I'm going to name it shadow variability. Give it a description. I'll pass on that for the demo's sake. And then we can specify how many runs we want to do with this. So if I just wanted say 10 example images of what this could potentially look like, I could put in 10 here. Or if I wanted to every possible combination of these different types of times and dates, I can do 10,000, and that's just going to inform how many images we get out of this. So I'm just going to do 10 for demo's sake, and you can see when I hit run, it's going to populate this over here. So we can see the number of instances that we're utilizing. These are our AWS EC2 instances, and you can see that some of these are starting to get assigned, and we're starting to churn through this data generation task. And then we can start to see that we've got an end time estimated. So 2:32 p.m. 4 minutes from now is when it looks like this will be done. So that's how we can kick off a job, and then we can go over and see some of the data sets that we have here. So if you used that content code, you'll get 4 different data sets, example data sets that are included with that content code. One is similar to just an example of various images generated in these contexts. So you can see here that we've got some buildings, and they've got some HVAC units on them. These are just some preview images of what's within that data set. So you can see here are some larger and some medium-sized HVAC units here. We also have some data sets that show the impact of changing the color of these, for instance. So applying different modifiers to your that's good. So adding different modifiers to your input 3D models can show you what the impact of modification of these objects are. Yeah.
Newbie question. In generating this example, you loaded XView data set as well. What is actually in the output here? What is actually being synthesized or rendered? What actually comes from the data set? How do they?
So that's a good question. The question was, what is actually being synthesized or rendered in these images? And so, as you can kind of see here, we've got a building in the background with some objects placed, some HVAC units placed on top of it. So in this case, what we're doing is we're placing these 3D assets on within an existing 2D background, so an actual that XView imagery, and using metadata that we've associated with that, the placement areas, the time of collection, things like that. We can simulate those 3D assets seamlessly within the 2D environment. So those HVAC units are what is being simulated within this. And then we have a couple other, for instance, various different defects. We can simulate things like rust or snow or these other sorts of things that we would potentially expect to see in our imagery. And then you can see here, this is the data set that we just ran. So this has 10 different examples of shadow variability. So this is where those HVAC units may have shadows that don't quite match the background. So we want to understand what that impact, what sort of impact that might have on our output training. Okay, so I'm going to go back to the slides here. So I showed you how we can configure our data set within this type of simulation pipeline and run the job management and create our library of output imagery. But we're not quite done yet because we want to then be able to configure our annotations. So we want to say, I had a huge list of input 3D assets that were going into that channel. By default, it's going to output each of those objects within that scene as its own different type of label. So if we go back to the graph and we see, we can see all those various different elements here that are going into it. We can then see, okay, what are these labels going to show? And it's going to, in this case, it's going to show up as some pretty uninformative names like L System 1, L System 2. But what we can do is we can convert those annotations as a post-processing step. So over here, we can see in our libraries tab here, we have this annotations microservice. And if I go here, I can convert this to a variety of different industry standard formats. So by default, we just output a kind of a catch-all annotation format that has all the different information that you would need, such as 2D and 3D bounding boxes, pixel level instance segmentation, obstruction amounts, things like that. From that, we can convert to all these different industry standard formats. So for instance, if I want to output COCO formatted data, I can just click on the COCO format tab. And then it asks for a mapping file. So in this case, the mapping file is essentially just a way to map these different values to a certain type of label. So here I've opened up what that mapping file looks like. I've listed the types of classes that I want. Really, I just want one class. I want to show HVAC units as an entire group. So here in this properties tab, I've got it so it looks for that object type, and I've listed out all those different names and what class that should map to. So I've deployed that mapping file as this one called HVAC. So I can then just click create, and that is going to convert those annotations to the COCO format, and then convert all those labels to match the different classes that I've set up for this. And then what you can see here is, if I can get to the top of the screen here. So I've added this into a notebook just so you can see what those labels look like in the imagery. It's taking a second to load here, but you can see when I upload those images, you can see this is an example of that, of one of those images with both the bounding boxes and the semantic level segmentation applied to it. So that's all in COCO format. Cool. So we've talked about how we can configure our annotations and build them to our own spec. And then let's see that we kind of discussed that. The next thing is we want to be able to post-process our data set. So we talked a little bit about domain adaptation, and you know, we can simulate things, but in many ways simulation is sort of an approximation of reality, and it's really what's happening is we're simulating what a sensor is picking up of that 3D modeled reality. But a lot of these sensors have their own specific characteristics, certain types of aberrations, certain types of you know, brightness levels, things like that. So what we can do is we can train a domain adaptation model using the source set as our synthetic data set that we've generated, and then our target set using a actual real data set that is going to that we can train to adapt those characteristics to match a specific sensor's output. So the model that we use is the CycleGAN domain adaptation model. It's kind of an original domain adaptation model. Does not require match pairs for training, so we can actually use you know, somewhat different data sets of various different content, but it's going to actually the translation that it's going to apply will trigger on the edges found in those images. So it's not actually going to really impact the fidelity of our annotations when applied to those features. Some of the considerations for when you do train the CycleGAN is that your source set should be your target set should be extensive. So we want to be able to map to an extensive amount of real images, and that's we find that about 1,000 images is kind of a good target for that. You can see some examples over here on the right. On the top right is 1,300 target images. Bottom left is 290, and the bottom right is 61 images. So you can see the quality start to degrade as we reach those lower numbers of target images. The other consideration is that the source and target should have similar objects present. Yes.
Can you guys, since this is such a critical topic, can you guide us a little bit more on how this works? For example, I try with some data, I train it on my problem, but then I have real data validation set, and I notice that it doesn't work as well as in the training set. At that point, how do I use this to try to do better in the validation set?
So what you would do is you would generate synthetic data. You would generate it to the point where let me just let these people in real quick. Sorry. You generate to the point where you're happy with the results, but then you want to actually do that domain adaptation model training. Then you would generate a large set of synthetic data. You would use your real data as the target set and run this CycleGAN model that is an open source model.
And so this CycleGAN is going to try to be not able to distinguish between the synthetic and the real data.
Right.
But the thing I'm not clear about it is typically you given an image that is, you given an image that is real, another that's synthetic, and then the cycle guy, the discriminator is gonna try and say, oh, okay, I can tell apart the synthetic from the real. And then you try to generate, you're gonna try to transform the synthetic images so that they look more and more like the real ones.
That's right, yeah, so, the question was, how you essentially do this, and that is to train that model to generate, to adapt that input image to a point where it can't tell whether it's from the source set or the target set.
Can I make a couple of extra
Yeah,
comments?
go ahead, so.
All right, yeah, as you say, it's a critical part of the process, and it's not uncommon that you don't want to stick with just the raw output of a simulator. So just a couple of comments. One is, there are times where you can use the raw output of the simulator. They tend to be circumstances where the objects are relatively large. So when you have a large number of pixels on an object, the domain matters less for detection. When you do see this as required, there's two ways that we start to see the need before you run into just failure of model performance. And Dan's going to show one of them, so that using UMAP analysis and starting to understand the embedding space and latent space of your imagery can be helpful. We've also found patchwise FID can be a great way to sort of understand whether or not you're matching well. So a couple of things about either of these approaches. Excuse me. So then you want to apply domain adaptation. We've been talking about GAN-based. There are also diffusion models that can be used for domain adaptation. Right now, GAN-based is available on the platform. It's sort of a single click so that you get that sort of history and that tracks where the data set came from. We'll be implementing diffusion in the future. No matter which one of those you choose, you want to make sure that you are in fact improving the outcomes. And so again, sort of tracking where the latent space changes is important. Also, no matter which one of those you choose, you don't need a labeled data set, which can be really crucial. And it's doing it with a corpus of imagery. So it's not as if you need paired imagery, right? You're not saying this is what it looks, this is the exact same thing in these two domains. You're just saying, take something and see if it would match as a set of this imagery. Okay.
Okay, cool. Thank you for the questions. So those are some of the considerations to think about when you're training a cycle GAN specifically for synthetic data domain adaptation. Now I'm going to go into the next topic here. The next task that you would do as a computer vision user is you would want to test the data quality. One of the things you want to do is run some simple analytics. So where are the objects found within my imagery? What is sort of the standard size of these objects? How many objects are we finding within each of these images? Just to get kind of some summary statistics about our data set and how that might impact, how that might relate to my real data. Yeah, go ahead.
When you're running those analytics, is it possible to indicate that the synthetic data contains examples which are unrealistic and might, because I mean, there's a randomization process when you're generating synthetic data, so it can happen that you're at some point generating data that is actually not valid.
Yeah, so that's a great question.
100,000 images. But are these analytics that you're running actually capable of noting them?
That is a good question. So the question was, when we're running these analytics, can it actually tell us whether our data is unrealistic or not in line with our real data set that we're looking to compare against? And that would go into our next topic here is data set comparison. And sort of the question we have here is how do we assess the quality and completeness of synthetic data? So, when we're doing it when we're creating synthetic data to improve computer vision models, you know, the AP scores that we achieve from that data is going to be sort of our, you know, yes or no north arrow of, but that doesn't necessarily highlight where are we missing? What are the pieces of the elements of the data that are not in line? What can we do to then improve that data set? So what we've found is that viewing these data sets in actually embedding feature space, so viewing sort of how those are seen from a neural network's frame of view, can highlight those sort of areas where we're missing the mark with our synthetic data, and areas where we have actually real data that is not well represented by our synthetic data. So what we do to do that is we actually run those data sets through a pre-trained neural network, a generic neural network trained on the COCO data set, so 82 different object classes, sort of a generic feature detection algorithm. And then we take the features found within those images, and we then use the UMAP algorithm for dimension reduction, and we take those feature vectors. So when we're running them through a neural network with a feature pyramid network, those are going to be various different sizes of dimensions. So we'll have 4x4, 8x8, 16x16, all the way up to 64x64. And then we can actually use UMAP dimension reduction to reduce all of those down to 3 dimensions. And then we can actually plot them within a 3D plot and see some of those trends that we can, that might highlight the actual embedding space. And I'll show you that right now. So let's go back to our data sets tab here. This is actually a different workspace that I've constructed to kind of highlight this specific sort of analysis that you might want to do. So we're still working with XView. I've uploaded a data set of XView. So not only can you generate synthetic data sets on our platform, you can also upload real data sets, to the platform as well. And that can be useful in this sort of data set comparison sort of framework. I've also have here a synthetic data set of about 400 runs that I have generated containers and tower cranes within these various different image backgrounds. This is actually relevant to a phase 1 SIBR that we did with the NGA and orbital insights, where we were looking to improve detection of tower cranes using synthetic data. And so we kind of have a history with that. And then I've also, as you can see here, one of these post-processing microservices here is to run a GAN data set. So if I select this synthetic data set and click here, I can open up the GAN post-processing microservice here. I can select, this is the XView GAN that I've trained here, and then you can give your data set a new name and create that data set. But I've done that already here, and this is the output. So this is that same data set, same synthetic data set with that GAN applied. So you can kind of see, if we look at the XView data set again, you can kind of see that it's kind of a darker, more reddish hue to a lot of these images. A lot of them have sort of some aberration, some artifacts that might come from this sensor. And if we compare the pure synthetic to our GAN adapted synthetic, you can see we've got some images that are a good bit darker, sort of more sepia tone, more reddish in hue, and have some of those aberrations that we've found within those. So we can run some analytics here. Yep. Oh, yep.
Maybe you're planning to talk about this anyway. Does the SAR, the hyperspectral one, work the same way? As in same workflow, you load up a data set and you add stuff to it and you do GANs to mush them together?
So yeah, I think that's definitely there are some caveats there. So with hyperspectral, you are working with large data cubes rather than kind of that 3-band imagery. So we would have to be able to account for that's the domain adaptation for that that many bands. And also, things like SAR, you would need to think about that as well in terms of
Can I jump on
Yeah,
that?
go ahead.
Yeah. We've done some of this work on SAR and shown some model improvement by using this. We're doing that on the final imagery. So those of you maybe not familiar with SAR, you start with that raw radar imagery. You produce an image by going through a process called compression or image formation. If you take that imagery out, you can do GAN-based domain adaptation with that. Hyperspectral, of course, has a lot more bands. The tool, as it's configured on the platform, is a 3-band. It's configured for 3, but the cycle GAN itself is actually, that's a flexible parameter, so you can adjust it as far as you want. So in principle, it should work, but we haven't experimented with GAN-based post-processing in hyperspectral.
How much meter rates, for example, all GP and you want to go to IR? Is that doable?
So that would be, that would be introducing some new information, right? So you would be predicting things like infrared using strictly GAN-based.
Yeah, you can, and people do, but there is important information loss. So that's not usually what we would do. And let me give you an example, right? If I built a GAN and I have a bunch of images of cars as they're driving, right? And then I look at that in infrared, all of the car engines are going to be hot. And if I use that GAN and I do the same thing to try to image a parking lot, I'm going to get it wrong because it's going to assume all the engines are hot and it's going to paint all their engines hot, right? So you actually don't want that. What you'd prefer to do is capture the relevant physics for the sensor that you're going to use as much as possible, and then use the GAN really only to capture the ineffable character of the sensor. Does that make sense? Yeah. Okay. Yeah. So I guess to kind of round that out, like our preference, some of this is, of course, philosophy and approach to engineering. Our preference is to capture as much as we can in the physics-based simulation, because then you understand how your definition of the environment is translating into the imagery, and to only use generative techniques for capturing those things that are that we were unable to capture via physics-based simulation. Because the more information that we get from the physics-based simulation, sort of the higher the fidelity is, the better the traceability is, the more that you can really understand what's being shown in the imagery.
Does your current platform stand up with you right now? That I can go and select different features of my object, for example, engine should be out or not, and then that generates IR directly without cycle GAN. I can just use at the end change a bit of randomization.
Yeah, we do infrared on our platform. When we get to Matt's part of the talk, he'll get into, okay, let's say one of the nodes that you want isn't there and you want to do something new. How do you do that? And that's where you get into synthetic data engineering, and you sort of he'll talk a little bit about how you might integrate new types of simulators or new types of effects into a particular application on the platform. So it's an important question. I want to reiterate one more time, or rephrase what you said. So in the way that we would think about it, we have a lot of different applications on our platform, right? I walked through maybe a dozen different applications in the platform. And in general, computer vision is a like long tail application space. It's just all sorts of different things, different sensor types, different domains, et cetera. So what we've done with our platform is rather than try to have one tool that does all of that, we've tried to build out this tool set that addresses synthetic data broadly. And then we deploy these applications for a particular need. So like Dan has shown a few different deployed applications associated with satellite imagery. The other side of the flip side of the computer vision user workflow that Dan is showing is the synthetic data engineer who might be actually creating that environment to begin with. And Matt's going to talk about that in a little bit. Hopefully that's, as clear as mud. Maybe by the end, it'll make more sense too. Okay.
Okay, thank you. Yeah, and that's a good point, Nathan, that, you certainly can use domain adaptation. I think, we encourage the use of the experimentation with, using domain adaptation in a variety of different ways. You can generate images of apples and train a GAN to and apply a GAN to convert those to oranges. But if you really what you want is images of oranges, likely the best way to do that is to create a channel that will output images of oranges directly. And that will tie into some of these things that's showing later. So yeah, so I've generated some satellite imagery, non-adapted. I've ran that through a GAN that I've trained specifically to adapt from this synthetic imagery to that XView data set. And then I want to actually compare, what sort of effect that has had on my output image data. So what I can do here is when I select more than one data set here and on the left, I'm able to click this compare data sets function here. And it's going to prompt me with the ability to choose the fit data set. Typically, we want that to be our real data set. We want to fit that dimension reduction algorithm to our real data set, and then compare how our synthetic data sets then compare with that. And then we can click compare down here. It takes a few minutes, so I've done that already. If we go down here to the UMAP analysis post-processing tab here, we can open this up and view that 3D plot. So it's opening it up. And here we can see this is a plot of those three data sets run through, again, this is run through a pre-trained neural network. The features are being, the feature vectors are being plucked from that neural network, and then using dimension reduction, reducing those down to 3 dimensions so it should be plotted. So we can see here on the left here, we've got our legend, the RGB satellite, the non-adapted satellite imagery are the green dots here, and we can see they're mostly huddled down here in this corner. We can see that our XView data set, our real data set, is represented by these blue dots here, and then the orange dots represent our domain adapted data set. So we can see right off the bat that using that domain adaptation technique has brought from an embedding feature space standpoint, brought those more in line with our real data set. But then we can actually inspect a little further. So we can actually click on each of these dots and see what sorts of images those represent. And so if we go over here and we actually out a bit at the page level to see this. If we go over here, we can see, both in the GAN adapted data set and the single data set, the non-adaptive data set, we've got some images in our real data set that are not that are outside of cluster. So these are images that contain features that are not represented in our synthetic data. So we can actually inspect and see, you know, what's common about these images here. So we can kind of see these are pretty dark images. That might be a factor in why they're outside of cluster. We likely didn't generate specifically super dark images. But that's a way we can actually inspect and see, you know, what is present in our real data that is not present in our synthetic data, and what can we do to change our simulation pipeline to be able to account for them.
Yeah, so to go back to the infrared question, right? Like cars that were, if you train again to convert all the cars to have hot engines, then you're going to be able to use this tool to identify, oh, wait a second, but here's some examples in which the GAN didn't take us to all of the regions of the space that you would need to capture. Right. And so what you can do with this analysis is say, is there something we need to do to update the GAN, or is there something we need to do to update the channel and to generate, to actually introduce new content?
How can we use this to say, okay, here is the problem with the synthetic data, still not working on, what do I change?
Yeah, so it's kind of a way to have a human in the loop of in the embedding space to actually look directly at this. And so we're looking at a single feature size in that feature pyramid network. This is kind of at that 4x4, so some of those larger features found in here. We can then inspect different sizes, different scales of features found within these different data sets at these various different feature sizes. And so we can do that same process of looking at the outliers at these various different scales, and we can see, okay, these are the sorts of objects or sorts of characteristics, right? Because it's not necessarily just objects, it's actually characteristics of the image as well. These are sorts of characteristics that are you know, outside of cluster, not well represented in synthetic data.
Yes, as far as we know, the human brain is still state of the art in this particular domain.
Sorry.
Sorry, as far as we know, the human brain is still state of the art in this particular domain.
Can you take a point like arbitrarily in this embedding space and create an image from that to get a sense of like intuition about the different axes in embedding space?
So your question was, can I take a specific point in the embedding space here and create an image from that? Is
Yeah,
that,
because I mean, all of these are like go from like very high dimensional images to like a low dimensional embedding space. So can you like take a point in embedding space, reverse that process, get some kind of like understanding of the intuition about like instead of having to pick through, like you could examine like what the extreme one is like on one.
so that's an interesting idea, to be able to actually take that and then essentially use the generative process to take that embedding point and then generate it.
Yeah, I mean,
an image from
Yeah, we
it.
haven't tried to do that. Obviously, there's some information loss in going from the picture just to the 3D point. So you'd have
sure.
lots of different pictures that could all map to that 3D point.
One of the features that we are working on is actually applying the spatial attention maps as kind of an overlay here. So rather than clicking on a point and just seeing the image, you can actually see the a heat map of where that neural network is triggering within the image. So you can see, you know, in this case, it might be this vehicle here. It's triggering that feature was being pulled mostly from that point, that part of the image, and then we can get more information about that. So that should be coming soon. But yeah, good question.
I think that
Yeah.
I mean, it's really cool. I really like the idea of this line cycle and just make this small difference.
Right.
But can it happen that we use the synthetic data system or generation of synthetic data to generate something that we don't have? So special case.
Mhm.
And now you go with those special cases and you try to adapt them to regular case. Can it happen that you then lose this actually this special case that is generated because it will say this is special case, it was not found in any of these, let's pull them down.
Yeah, it's an interesting point. I mean, if you don't have data for the specific kind of thing that you're modeling in your synthetic data, how are we getting information about that? And I think this is more to look at like the general characteristics, the things like the aberrations found within a sensor and those different cues. And if we're generating synthetic data and we're not matching up there's going to be a disconnect in model training. If our embeddings are not in line with those of our real data. I don't know, Nathan, do you have any other thoughts on that?
I mean, maybe part of the question was if we're building synthetic data sets to handle rare events, do we deteriorate the performance on regular, non-rare events?
Yeah.
And you can, there's a lot of ways to screw up. So one of the things that can happen is if you had a model that doesn't have any rare events in it and it's failing, and then you do a post-processing training or you do fine-tuning using synthetic data, you can skew it, especially if the domain has a gap. Matching the domain certainly helps with that. I think probably anybody in here who's trained a multi-class detector knows that there's sometimes some trade-offs between performance across different classes. Usually what we find is you're trying to not eliminate, how should I say, what you're trying to do is engineer sort of your bias among the different classes, right? And yeah, there's usually some trade-offs, and there are approaches, of course, to using multiple different types of detectors if you really want the highest performance across all classes. I don't know that we have a better answer than that, but matching the domain is certainly really helpful if you want to avoid biasing the system towards synthetic data, which is really easy to do. So if anybody here has not played with synthetic data, if you use something that's sort of straight out of Unity or straight out of Blender, you'll almost inevitably be super biased if you're doing any kind of small object detection. And so this kind of domain adaptation is really important to avoid deteriorating performance in other classes.
Yeah. I think the take home point from that is there's a lot of ways to screw it up. but we're trying to show some ways that you can avoid that. So cool. Any other questions before I move on?
Can I say
Sure.
a bit of a question? I appreciate stylizing the synthetic data to match the domain of the real data. But can you use this at all to sort of find where there are the gaps in my real data set that I need to add some synthetic data to fill in? Or is that just, I should know that I don't have enough images of black swan, so I need to generate some so I can detect them? Or can you, look through the data set in this sort of feature space?
Yeah, maybe I could jump on this one, Dan.
Sure. Yeah.
So you can, but I want to be a little bit careful. We've sort of made product decisions intentionally not to try to become an overall MLOps, everything you want platform, and focus on synthetic data. So the way that we would approach that problem is you might say, do I have a problem here? I want to detect stop signs. I'm a little bit worried about whether stop signs with ivy on them are in the feature space of the real data set or that's different. So maybe I would generate both. I would generate synthetic data that had stop signs with ivy on them, and then I would take a look to see if that was a very different feature space than the ones without, because that would give me an indication that then I'm going to have trouble with detection, right? there are platforms that do pure, embedding analysis of a real world data set and try to identify gaps, but it's always a question of gaps relative to what? Right, so synthetic data is a way to constructively pose that problem, but it does require someone to say what the what is. There's some real information in the domain of things that you're interested in being able to find and detect in.
What if there is no real data?
So-
And I'm gonna go pure synthetic.
We
Have 3D models of different objects or to start with.
we have thousands of 3D models on our platform. Even in what Dan's showing, actually, you can also bring your own 3D model. So if you guys get into this and you're like, hey, I don't care about HVAC systems on top of buildings, I'd like to find toy trucks on top of buildings. Great. You can actually bring your own 3D models and drop them in using only the graphical user interface. So that's possible. And for those of you maybe not familiar with sort of this space, but there's websites like TurboSquid and others that you can actually go and get 3D models for almost anything you could imagine. So a lot of that content exists. And increasingly also you can use generative techniques to produce those models as well. So that's sort of up and coming, and we'll be integrating some of those capabilities into the platform as they mature. I'd say still a little bit immature to rely on just yet.
But the background is still from the fashion, right? So 3D models, you can make it, to customize it, but add it. But if you do not have the real data, that means that you do not have the background in there.
So So that's specific to this example. So a lot of what we do is actually fully 3D and fully 3D environments with no real world backgrounds at all. It just so happens we're showing some examples in satellite imagery because you tend to have backgrounds available. It's a powerful way to get a lot of the diversity in the real world. For instance, in synthetic aperture radar, those all are simulated 100% synthetically because we need to simulate a fully 3D environment. We can't use a 2D background for radar images. Similarly, actually, most of what I showed was fully 3D and when I walked through the different applications. So no, you don't need to have any real world data at all to get started. You can do fully generated. And we work with applications sometimes where there's none. Usually there's some because you're trying to detect on something, right? Like if and the exception to that is if in fact what you're doing is building pipelines for something that doesn't exist yet. So the work we're doing with Planet, for instance, that's for their next generation satellites. There is no real world data for those satellites. So what we do is we generate scenes. We actually build out hyperspectral content across those scenes, including behaviors.
And order, for example, that kind of scenario you need and you can make it.
That's right. Exactly. Yeah. Okay. Does that answer your question?
Yeah.
Can I get to it? Okay.
That's all about, you must have that real scene available to upload it and stuff.
Yeah, the 3D models on top of 2D backgrounds are a powerful technique for a particular class of synthetic data. So we use them where that's appropriate, and where not, we do fully 3D or other generative techniques to create the environment.
Cool. All right. Let me move on. Thank you for your questions. So we talked a little bit about this, but we want to be able to incorporate our synthetic data into our MLOps pipeline. So one of the ways we can do that is through the rendered SDK, and this is called AnaTools. You can download it off of PyPy here using just search for AnaTools. There it is, and from there you can do everything that you can do within our graphical UI, and then some using the SDK. And so things like creating graphs, modifying graphs, generating data sets, uploading and applying GAN models, running these sorts of analytics, and then building those annotations can be done programmatically through the SDK. And I'm going to show you quickly what that looks like. One of the ways we can look at that is by going to our documentation page there. So if you didn't see that, I just went up to this question mark here and went to documentation.
Good.
Okay, so go to documentation. And that's just to support that render.ai. And here we have some areas here around the actual application user guides. So how to use the web application, how to do your own development on the application, and then some sort of general concepts and release notes about the platform. But up here at the top here, we have our SDK documentation. And this is the kind of single source of truth for our SDK, and we can look at older versions, but we can go in here and see all the different functions that our SDK provides in terms of all these different packages here. And then we also have some notebooks, a repository of notebooks that kind of get you started using the SDK, doing some common tasks with that SDK. Here, and then another thing that is coming to the platform coming soon is the ability to pipe directly into SageMaker and run SageMaker experiments using your synthetic data. Nathan, do you want to show that? Is that something we can quickly?
Yeah, I think just for time, maybe I'll just describe this. So one of the things we found with a lot of our users is they do want to rapidly train models, but they have their own MLOps pipelines. And so we recently partnered with AWS to allow our users to create SageMaker jobs in their own organizations, so in their own environments, but task them from ours. So you can actually link your rendered account to your AWS account and then kick off SageMaker jobs from your rendered account. That's going to be released here in the next couple months, but what we envision being able to do is a lot more experiments around things. There's some really basic things that almost everybody needs to do with synthetic data, like figure out how much you should use relative to your real data set, right? And so you want to be able to sweep through that space, understand what's going on. That should be a really quick and easy job to do. And so that's being implemented as an example. Some of the things like training GANs or maybe training diffusion models are also tools that we'll be putting up there and allow people to spin those sorts of jobs up in their own environments. And we do that so that, you know, we don't have to have a billing pass through to AWS, but also because a lot of people are sitting in environments where they've already got, you know, large amounts of committed capital in those cloud environments.
Is there any QC/QA process in the pipeline at some point?
So right now what we have is that UMAP process. So that allows, it's a human in the loop QA process where you can go in and analyze the embedding space of your synthetic data relative to real. We're looking at some ways to automate that more, but like I mentioned, the human in loop remains sort of best in class for that technique right now, if what you're trying to do is understand. The only tool that I'd say we'll probably implement soon is a patchwise FID. So you're familiar with FID scores? So you can do that on a patchwise basis, and it can give you a strong indication as to whether or not any particular image is, let's say, out of domain or out of the group.
More, I'm talking about visual. You say when there is a, for example, occlusion, but object is behind the other object, and it doesn't detect. You know, you see the annotations, comes to the data, you don't realize it.
Yeah, so we actually include obfuscation in the annotations. We did a study with NVIDIA, really looking at, you know, how much, if you train, for instance, on data that doesn't have much occlusion, and then you try to test on levels of increasing occlusion, how does the performance start to degrade? We did a white paper with NVIDIA on that. I can share that with you if you're interested. But that's embedded in it. So one of the things you can do is if you want to, for instance, exclude annotations for things that are heavily occluded, you can.
Yeah, and you can actually build kind of custom annotations based on the actual metadata that we supply as well. So if you want to look at, create a new class, for instance, of cars with snow on them, for instance. That's sort of a modifier that is applied to a 3D model, but we can see, looking at the metadata associated with that data set, where within those data sets are those different modified objects, or and we can also calculate as part of the annotations that occlusion certain industry formats like Kitty contain information about occlusion amounts present in that data. All right, one last thing I'll talk about is that last step, the experimentation. You want to be able to easily add content, add modifiers, and extend your channel to be able to understand, get a better understanding of what the impacts have to that. So one of the things that Nathan quickly mentioned was the ability to add 3D models directly to the platform, and I'll quickly show you how we can do that. So here within our libraries tab here, we also can see the analyses. That's some of the analytics that we run, such as UMAP or other analytics. And we also have the volumes here, and this is volumes are essentially a cloud-based storage protocol that allows us to add new content directly to the platform. And if we click into here, we can see some of the content that we've added here. So this is a in-ground pool Blender file that I've added. That is just something that we've acquired and added here. So in the cases of looking for HVAC units, you may want to be able to differentiate between a rooftop pool and a HVAC unit. So here within that demo volume, here's the way you can upload files or even create new folders. But I've uploaded this Blender file, and if we go into our graphs and go back to that graph that we were looking at, we can see over here in our content pane here, we have the content that's deployed to the channel, but then we also have the ability to look within those volumes and add that in-ground pool feature directly in here. So we can add that in as another node to our content that is going to be placed on those roofs. That's just a simple way to add some new content to a channel. There is a lot more you can do in terms of channel customization, in terms of new modifiers, new placement algorithms that fall into the role of the synthetic data engineer. And so with that, I'm going to hand over to Matt. We'll take another 5-minute break, but after that break, Matt is going to pick it up where I left off here from the perspective of the synthetic data engineer, and show you how you can create very customized synthetic data using the render platform.
Go even further down the rabbit hole.
Yeah,
So let me
I mean,
make you
after you only gets so far. Oops.
So I'm going to make you host, Matt.
Yeah.
Okay.
And you're gonna share directly from your computer? Okay.
I am host now.
Is there any study around the efficiency of synthetic data generated by your platform? Not in the sense of photorealistic, if it is in the sense of neural network performance against real data.
Yeah, for sure. Yeah, but usually what we're doing is comparing like, how should I say? The circumstances where it matters are in ones where just typically a small amount of real data or no real data. So what we end up doing is saying, hey, if I have synthetic data, what is the equivalent amount of real data I would have need to have to get to equivalent, to get to the performance of like, say, synthetic data plus some small amount of real data? Does that make sense?
Yes, but the quantity is, I would say, is less important. and randomization.
Yeah, that's right. So, and it's almost like you could do an experiment with just like number of images synthetic versus number of images real, but as you say, it's a little bit misleading because it's like, that's not necessarily what's important.
Yeah, let's say you, I think a good probably ablation study is that you grab your UI and saw whatever data simply train model on that, and then you grab the same model training real data, then compare the performance of these two against the benchmark data set, and to see.
Can anybody hear me?
I think all the real data is closer if we have.
Yeah, if you have plenty of labeled real data, then.
But
then
let's say with synthetic data, we got to almost 90% of real data.
Yeah,
So that kind of ablation study.
we've done that. The place where you see synthetic data really benefit, and if you want to do a comparison, is you say, okay, let's just take a class like maybe have pictures of cars.
Yeah.
But we pretend that it's rare, right? We pretend we don't have many pictures of cars. So what if I only had 100 pictures of cars and I had as much synthetic data as I wanted? Because usually synthetic data is sort of cheap to build. What is the equivalent number of real pictures of cars that I'm able to achieve? Right, I only have 100, so how far can I go? And what we find is, you can get like 100x plus improvements. So, I only have 100 images of cars, but I'm going to perform as well as a model trained on 10,000 images. Does that make sense?
Yeah. After a bit of a study, we can share.
Yeah, that'd be great. Thanks.
I'm always scared when it's too easy.
Uh-oh. Yes. We should charge at the door. It's like $5 in and out, no matter what, every time we open. Yeah.
Can everybody hear me on Zoom? The remote folks. All right, thumbs up, thanks. Are you logged into the meeting?
Yeah, yeah.
Right.
All right, do you want to bring it? You want me to bring people back in?
I think we need a pot of coffee for this part of it.
Yeah. All right, guys, I think we're going to kick off the final part. You're going to continue down the rabbit hole with us just a little bit longer here. And the goal in this last part is actually going to move a little bit outside of the domain of most computer vision users and talk about the other piece, which is who's actually implementing the physics simulation, right? And how does that happen? And I think we wanted to include that in this tutorial for two reasons. One is because we know there are people here that have a variety of different types of expertise. But also, just, I think it helps drive the point home about how far you can go in terms of configuring content on the platform. And so Matt is coming to us with a physics background and has been overseeing things like implementing X-ray simulations and hyperspectral simulations and all sorts of really great things for some of our customers on the platform. And so you're hearing from really one of the experts in doing that, and he's going to show you a little bit about how the magic is done. So.
Yeah, thanks, Nathan.
Adam, I'm getting word that there's a bit of an echo.
Oh, yeah?
let's See if I can.
Let me try one thing. Or well, we have two microphones, or or maybe three.
Let's see.
But yeah, okay, thanks, Dan. Let me try one thing. Oh yeah, are you on mute now, Nathan?
I just muted.
Okay. Do we still have an echo?
Okay, it's better.
Okay, okay. Yeah, great. So just to jump right in, we're going to add a feature to a channel. And so first I will walk through creating a workspace on Rendered AI that contains our Toy Box channel, which is a channel that we have open sourced on GitHub. And then walk you through setting up the development environment and reviewing the code to get a sense for the architecture there. Then demonstrate running the channel locally, how you would test it, modifying the code, and then deploying it to your organization and previewing the results and seeing the change on the platform. So to get started, let's head on over to Rendered AI. Can I have my phone? This part of it requires you to make sure your email is legit. So what I'm gonna do is click get started here. And the idea here with this whole presentation is that we can make it, is that it's just as easy as sitting down for 20 minutes and going from start to finish. Let's see how far it goes. So I'm gonna say my email is Matt plus CVPR 2023. Just as a new email that the platform doesn't recognize. Except that, yeah, this should work. My name is Matt. My company name is Computer Vision Scientific. And I will just go, yeah, so filling out, given the platform some information about what kind of person we are. Just going to say I'm a data scientist working in the aviation industry, and that I don't have any experience working with RGB for a satellite. And I'm going to click Python because I can't help click the top one all the way through when I see that. And then sign up. So let's see here now. So that created my account, right? So isn't that right? There's two things that it does.
Yeah, that you're creating your account now. Yeah,
Now we create the account. Okay, right. That was just to pass through. Yeah. So again, Matt. Let's see. This is going to actually be my account. You think? Yeah, okay, we'll try it. And then I'm going to enter Toy Box V2 here. So it's been mentioned that we have these content codes that pre-populate your account with content, and we'll share with you several of them shortly. But this one is what we're going to use to match the source code. Haha. Oh, that's right. I changed it. Now it's CVPR. 2023. Should look at my notes. Okay. Sign in. And now the security concerns. So I want to put you through this because it is just a minute. And I think there's a lot of comfort knowing that you've seen it gone all the way through the process before. So there we go. Also, I like to take risks live. So now I have a brand new account and a new organization. And as you can see, there's a workspace that already exists. So what I'm going to do is just kind of take a look through here and make some observations about what you get. So there's 4 graphs pre-populated in this workspace. We can go and look at them in detail. There's going to be some libraries that are pre-created. You can see that some jobs were run. Basically, this just clones a workspace that we maintain. So in particular, this that kind of the kind of the main driving graph that we have here in the Toy Box channel for sharing is this thing called Toys and Containers, where you can see several generators for various types of toys. There's a color variation modifier. So the bubbles, for instance, can take on colors. And then there's a Rubik's Cube that gets dropped in. We have an example of a weighting modifier for the graph. So this branch will be chosen 4 times as often as the one above. So we'll have the same number of Rubik's Cubes as as bubble bottles. The scene, so to speak, is driven by this placement node. There's a tooltip on each of these nodes. This one says create objects, containers, and floors, and drop the objects into the container. So you can get fairly detailed information per node, and that's something that we'll want to do in a minute, is to make sure that's accurate and an option so for the users to understand what you're doing, or for you to keep track at later on. This number of objects field takes in an integer, and I have a random integer node set to between 15 and 50 objects. So that'll be a randomization. There's a container generator that can drop in so we can specify a container, or we can have multiple of these nodes going into here if you want to have just boxes. But this one has boxes and tubs, and then there's some floors to choose from. Deeper in, regarding the rendering, the render node here takes in a field called lights, and so several lights can be added. Right now, there's just a point source with 100 watts at a particular location. These can all be randomized. There's a camera. I have a 50mm camera node here. Other camera nodes could be made. Other things could be exposed. It's parameterized by light, by its height and the rotation. And then in terms of the rendering, we can define how many pixels we want to gather, and whether or not to include the obstruction calculation into the annotations. So that's kind of the way a lot of these channels look. I think it's a nice kind of generic channel to start from. So I wanted to call out that there is this node catalog on the left, in which there's a hierarchy involved. So the modifiers are have a subcategory of color. Underneath objects, we have generators that, so these are all of the objects for this channel are generators. And there's like the toys and the floor and the container are in here. Under scene, there's 2 rigid body scenes to choose from. A placement, a random placement, and the place over container, like this one. Okay, and then the simulation node, just it has our cameras and lights and render. So let's see, one other graph to take a look at would be the toys on floors. And in here, it's basically the same. You have a bunch of toys, you choose whether you want 15 to 50 of them, and you have the same lighting and camera stuff, but instead it has this random placement node, which does not have or has a container as an option. And it says it creates object containers and floors and drops the objects randomly. So it's sort of like we have a messy option, or everything kind of mostly lands inside the box option. So what we're going to do is add blur to the render node. We're going to allow the renderer to add a. So this channel happens to be based on Blender as a simulation engine, and so Blender has the compositor built in to configure everything that happens when you do a render, and so it has a nice Python API, so it'll be pretty easy to code it up, and then the result will be that the render node will accept a value to configure how much blur you want to add onto the image. Another idea that we had for this tutorial was to drop in objects, like where Dan was talking about a little bit ago. And I want to mention that there is this custom objects graph that that comes here. So I went ahead and just dropped in an apple and an orange based on what he was showing you in the volumes, and then you just can drop apples and oranges in the box. I think then there's baskets in there too. That's a bug actually, yeah. But okay, so we can preview that if we like, but just wanted to point out that in our node hierarchy over here under volumes, we have a fruit and baskets volume that I just kind of created, pretending to be a user of the channel. That these are things that are not built into the code. They're something that was added after the fact so this is called a workspace volume, and it's associated specifically with this workspace. So step 2 will be to set up the developer environment. So show of hands, how many people have developed with Docker? Okay, more than expected. This is going to ruin my joke. How many people have have used VS Code? All right, so don't worry if you haven't. The workflow that we have here is specifically built to just get your hands onto the software components without having to become a backend developer and understand the ins and outs of putting together web applications. So I'm using my Mac here. It's not my day-to-day computer, but I really wanted to start from scratch. And so I didn't even have Docker in this thing. And I went and I actually wiped it all out. My kid was using it for school for a while, then he broke the screen and now it's mine again. And so so I went and just did I did Google Docker Desktop, Google VS Code, install, run, and was pleasantly surprised that I was able to just open up VS Code and grab the code. So here we go. Proof of failure. So let me restart the desktop then. let's see. Yeah, okay. So before we can pull the code, we need to go look at. Let me just point out GitHub and our what we have over there. I guess this is a good time. So Rendered AI has several open source, a few repositories. I think this is kind of the main one that we work with. And another repository we have up there is that resources repository that has the SDK examples. But with VS Code, you can just grab this URL. Or no, actually, no, is it URL? Yes. Or do we have to get the? I guess this one. I think no, it's from URL. That's right. So we just grab the URL. And now Docker is back up. That's what's going on. So I need to start over again. It's no problem. Code. Close a, how do you close a folder? I guess maybe it's here. So I deleted everything so that it would be fresh, and now it's complaining. Okay, so we go, it's underneath this source control option, clone repository from GitHub. Put in the URL here. Of course. All right, so let me explain what I'm doing. I'm successfully copying the URL and cloning a repository based on the URL. And now we're going to create a location for it. CVPR 2023. Select. Open. Yes. See how easy it is. Reopening container. So one of the things you have to do is add this extension to VS Code, and I've already done that, but VS Code will let you know that you have a dev container here. You can see that there's a directory that comes with the Toybox repository called .dev container, and it has our this JSON file which triggers VS Code to build a dev container specifically for VS Code. And the great thing about that is that you get to have a Python environment that is exactly used in the backend. So the version of Python and whether any CUDA libraries that we use, well, wait a second. So this will use the same base image that's used for the OS and the cloud, and then install AnaTools and any other dependencies that we need. So now, what's going on? Looks okay. So in my terminal down here, we can see that there is a, no, this isn't right. Please excuse, I have some legacy stuff here. This is an older, so this was just the version that I was testing with earlier, and I want to make sure that we're using the brand new one for the walkthrough. Yeah, maybe I can just take a moment as he's getting that together to sort of describe what we're showing here. The way that the platform is designed is that you can build these apps and then deploy them to the platform. But of course, setting up a developer framework can be painful. And so what we do is we host base images that can be used as the actual development environment. So if you go and you pull from the GitHub repo, there's a dev container folder in there that will automatically set you up with a complete development environment on your computer. And that'll work. It's also cross-platform. So what it's setting you up with is a Linux environment. So if you have Windows, you can use WSL2 and you're set up. If you're Mac, it's more native. And it'll also pull things like there's different base images depending on which simulator you're using. So in this case, he's using a Blender-based simulator. So it's pulling Blender for you. It's pulling all the dependencies to run. And that allows you to just get started and edit the actual application and then deploy it without having to go through all those steps yourself. Usually.
Okay, I'm gonna just open this one more time and then do the cooking demo.
Yeah, so if you're not familiar with the .dev container framework, it's saying, reopen in container. And what that's doing is you've got a base of code. It's opening up that code inside of the base image that it points to. So that also allows you to share folders in between your home directory, your local directory, and
Okay, so we have a version of this of the code up. So let's see. So I wanted to take a look at the structure of what you get, and starting from the very high level is we have this a file that is a .yaml file at the very top level in the root, and this is the channel configuration file. So what you get, so what this tells the platform is what there's a channel type option here, which we need so that in the back end the cloud knows how to call the container. And then there's a setup option to run any scripts that need to be run for setup. And then there's this thing, and then we add packages and we add nodes. So all of the channels are really loaded up, and all their content comes from packages. And the packages could be shared between other channels. They're Python packages, so we can look at the setup for them and maybe set versions on them. And then when you go into the requirements.txt file, it'll actually install that package as a Python package. Yep. And so this package has this channel has one package, and it's called example. And the important part of the package is that it has modules called nodes. And so what you get with the Python module is the logic that runs when they're executed, as well as the schema that we use to define what the inputs and outputs are in a platform. So yeah. So now we are ready to modify the code and to test it. We're going to modify the simulation module, which has, if you remember in the GUI, it shows that underneath that simulation category, there are lights and cameras and render. So those things are all set in the schema. So here we have, so for instance, this light node we give it an alias for it to have a nice name in the GUI. And then the inputs are defined here. There's we have some validation that is that can be configured to help the user know when the right things are available. And this is all documented. And then in each one of these schema for each class, there's a category and a subcategory, a color and a tooltip. So these are all to help the web tool place them in easy to find ways. So what we're going to do here is go into the render node here at the bottom, and we're going to add a new input. So right here, we'll add looks good.
So
Yeah.
as you do that, so what he's doing now is adding an input so that if you're a synthetic data engineer setting up this simulation space for somebody, they'll now get to control something new in that node-based framework that we showed before. Does that make sense? It'll become a new input to one of those nodes. There'll be something new to be able to program. Then we'll define what that does. So we'll put a new input on that. Then it'll do something new. And we'll deploy that to the platform and actually take a look at what it looks like.
So I'm going to call it a blur size to give it a name. I'm going to give it a default value of 0, so that if other graphs that don't have this input there, they won't break, because the system will just know, oh yeah, it popped. If I'm not holding anything, it should be 0, and then I'll require it to be a float. And then okay, and so save that, and then go back over to the simulation, and what we'll see. So let's see here. So here are all my executive functions. There's a light node that configures a light, camera node that configures a 50mm camera, and then here's my render node. Things that happen in here is it collects inputs and affects settings, and with all kinds of really great documentation. Let's see here. So I want to add, so it looks like this thing, there's already a denoise. So I'm going to put the blur after that. Grab this stuff, which copy it. So now the logic that we're adding here grabs the blur size input and uses it in this compositor node blur object, which I learned about from heading over to Google and looking at it in the Blender and finding out what kind of things I could do to make it to add a blur node to the compositor. So there we go. Save that. Okay. So before we did this, I should have run to make sure that you can see that it runs before we make the changes. There's 4 utilities that Anatools comes with outside of. So Anatools, the pip package has more than just the SDK functionality that interfaces with all of our APIs. It also has several common nodes. So like all the randomization nodes and the graph weighting node and things like that or general purpose are ready to go in Anatools. And those things are defined in that top level channel YAML file. And additionally, there's these utility functions that wrap a bunch of the SDK stuff into one line so that you can just call basic things. So, I mean, you can use the SDK to mount a volume, but it's a little bit clumsy. And so we maintain a function just called AnaMount that you get as a bash command when you're in the SanaTools environment. My font is too small, huh? Yes.
So you went over that pretty quick. Do you mind if I?
Okay.
One of the problems that you have in developing large synthetic data environments is that you often have large amounts of 3D models and background information that you need to be able to actually run them. So we store that on the cloud, but you still want to be able to develop locally. So somehow you have to be able to navigate that. We have a utility called Animount that does that for us. And so by running Animount, it's going and finding out what does this application actually need from our cloud-based resources, and then it's mounting that virtually on your system so that you then have access to it for purposes of development. So that's what he just did there.
Yeah.
We use Python as glue code. So the Python defines the interface with our platform, but then we use all sorts of things beneath that, including C, C++, interface is Python. Yeah, exactly. So we generally speaking tried to match to kind of best in class. Unreal Engine has Unreal actually has a C wrapper, right? As opposed to C++. Yeah. Blender has a Python API directly, but you can plug into any of those.
Yeah. So the Animount function is actually just is a bash script that's calling all this Python underneath. Might be a Python script. Huh? The author is here, but yeah. So all of these utility functions come with a help command, and so you can get some help. So you can get some ideas about what's available to you. In this case, we're just going to run it straight directly. And now there, we will, now this dev container is linked to the 3D content on the platform. And a helpful little tool to run a graph is just called Anna. And there's several things we can do for Anna. Importantly, level. We set the log level flag to info because that'll give us the same information that you get in the logs in the platform when you do a run. There's several opportunities throughout the platform to look at the logs. Buttons here and there, just touched away, and this will give you this will make sure that you get that information out. And then you can set which graph you want to run. So the code comes with the default graph. And now it'll so now the code is running and doing a single run, and it generates a nice output file here, which will populate with the run for this particular configuration. So under graphs, we can just while it's running, take a look. It lists the nodes. You can see there's the toys are listed here with various links and values. The weight node is in here. So it looks like it's very similar to the toys in containers graph. The number of objects is fixed. I guess it's not exactly right, but it's not exactly what's in the content code, but it's a great starting point. So where we have something that we can work with. So the change that we made to the simulation node accepts now a blur size. And so what we can do is what I'm going to do while this runs is I can leave it running. And then, so the default graph here, save as blur 10. And then go into my render node where their values are. Here it says calculate obstruction false. We're going to put blur size. Done. Okay. And then I'll be able to run this plot, this one, verify that it works, and then deploy it to the platform. And that's the way it looks. Yep. So yeah. Within the web tool, to be able to add this kinds of functionality, to change the configuration of the.
So we're adding more and more functionality that doesn't require code. But right now, so the first thing was you can add 3D models without requiring code. We are looking at being able to sort of like expose the code of a particular node and just be able to edit that. But right now, eventually you do run into a circumstance where, you know, the functionality of the application does need some code exposed. And so what we're hoping to do with this part of the tutorial is to show what that looks like if you do get into it. So just to kind of come back to the architecture of the platform, there's not one simulator for the platform. We work with dozens of simulators. So each of them will have different types of 3D content that they can accept. And usually though, there's exchange formats that work across them. So the platform doesn't have a limitation on 3D content, but some of the simulators that we have deployed in the platform do. Does that make sense? Yeah, so like you mentioned, we have an Unreal Engine integration, right? So for instance, if you want to create synthetic data with Unreal Engine and you're a computer vision user, you don't necessarily want to get into their C integration and do all the work. But there's people who are expert at that. They can wrap that using the Rendered AI platform, deploy that to the computer vision user who can then control it using just the node and edge. Does that make sense? Yeah. What we're showing here, the intention is to cover, so that user group that is expert in 3D modeling, this is how they can take that expertise, put that into something, and then deploy it onto the rendered platform.
All right, so where I'm at here is that we we ran the default graph. It looks realistic. So now I can run the blur graph. This is the, so it's running in the container on my machine that's mounted to the data on the platform.
The 3D models are coming to us from the cloud, but the rendering is happening locally.
Right. So the data right there, like the 3D model of the Play-Doh is coming to us from far away. Yes. Yeah. And GPU. Somewhat. I think the reason that I was running into problems at first is because my Mac isn't happy about the GPU sharing, and so I had to go and comment out that part. So now I'm on the CPU here. But yeah, yeah,
it's pretty generic. There's not any specific limitation. In fact, the reason that we've gone with the developer framework, which is a base container, and then you pull an image and open that up locally, is that it abstracts away almost all of the local requirements on your system, other than having sort of sufficient compute for the job. Now, you wouldn't want to generate 10,000 images this way, right? It would take forever. Right, but if you want to generate one when you're putting the tool together, you can do that locally, but without having to go and deploy it. Yeah, you do. So it's a pseudo mount. It's not a direct mount to AWS. It pulls it over.
You do have the space, you do need the space.
But you don't need it for all of your models. So if I have 100 gigs of model, it's not downloading all of them, it's just downloading the ones that I've got. Yeah, that actually brings us into a whole discussion about rendering pipelines. Not always. There, especially when you start to render sort of city-sized or geographic scale imagery, you often either don't want to bring the whole scene in, or you bring it in at different levels of detail. So in some of our rendering pipelines, we're very intentional about what it is that you're actually bringing down for that rendering, because you intentionally don't want to bring it all down in full detail. Most of our simulation tools use GPU as well, or can use GPU as an option.
So when you go to the container, you can decide.
You can decide to use the GPU.
Yeah.
That's right.
So we can develop on CPU with limited scene requirements. And then once we're sure that it's robust, then turn the GPUs on in the container and deploy it, and then it'll work with the GPUs in the cloud.
So out of the box, do you support this dynamic rendering, or is that something that's slowly done?
So that's sort of simulation specific. So the area that we run into that is with DeerSig, which is the hyperspectral simulation tool. And so we've been doing some of that, but that's not something that we've open sourced yet. If that's a specific, like building up rendering pipelines like that is of specific interest, happy to have an offline conversation about how to get you access. Yeah, fair enough. So you know all about LODs.
Showing Blender nodes and control like with Blender. What happens with the textures of it? So you just rely on the texture that is provided together with the geometry, or do you have possibility of fairly
To the extent that the Blender API exposes. I mean, it can be as transparent. This doesn't need to. Whatever kinds of opportunities there are to parameterize things within Blender through the API, right, through the Python API. Right, so you can go through and find all those lists and change things. You can relink nodes, and you can associate different textures.
fixed value, right?
May I
Or
jump
do
in?
you have a possibility of providing ranges?
I could take it.
Okay,
So
go ahead.
so with the node structure, there's I mean, you saw how we do randomization, right, with the node structure. And so those values are changed at runtime for every run. Right, so one run, it'll be a fixed value, and then the next run it'll be a different fixed value, and that value, and they're sent in. So that's why the objects are called generators, right? I mean, they're specifically not instances, but they are instance at runtime depending on if they need to be, and then at that time depending on then at that time inputs can be in for each of those generators.
At this point, so I would have to, let's say you want to model texture, this particular product that you have. So you would have to go to Blender yourself, do whatever you need to do to create your texture, and then pull it from render, from render data. You don't have any kind of possibility to provide some kind of term.
No, I mean, if like, so one option is that you have some static assets from your texture rendering app pipeline. Another option is that software is you can add it to the channel, or you can drop in those libraries that consume textures and then create the asset that's needed in the Blender file.
Would you at any, or at any point in your pipeline, anywhere, support any kind of procedural approach?
Yeah.
We do procedural effects on both the geometry and the textures. And so like specifically, like we have generators that introduce rust and snow effects, things like that, warping. And we've actually experimented with using generative techniques that you can actually, generate a texture based on text prompt and then mix that in with the texture that's resident. And so that could be helpful when doing things like, hey, I want this to look damaged or camouflaged or something like that. And you can get those textures pretty easily.
Okay, so I made it blurry. And then the last step is to use our utility tool called AnnoDeploy, which takes several interesting options such as whether basically I don't know, I don't want to get too much into these details. Actually, I just love the last one here because we get to push extra data to the cloud if we need to. Thank you for the support, product team. Yeah, so one handy thing is that the email and password can be sent in so that it can be built into pipelines, and we can allow people to deploy channels as part of a pipeline. But in any event, it's I think we can take a look at it. Well, no. So I think it's about 6 gigabytes, and we don't have time to upload that, especially with conference internet. So I will just head over to the to rendered AI, and
Maybe you could just type in AnnoDeploy so they could see it get started.
oh yeah, that's good.
Finish.
Yeah, there is some nuggets in here. Plus CVPR 2023. So this organization doesn't have any managed channels yet. So we're going to create a new channel, and we're going to specifically connect it to this organization. We have one organization because it's a brand new account. And then it says, do we want to use the example, this channel to go in this deploy process? And we say yes. And then we get to give it a name. So I like to give it some version number in case we make breaking changes later and want to and we want to make a change that would break the previous. Okay, and then I don't know. Maybe it was an authentication. Well, is this what we're looking for?
It's live theater, guys. Usually that works really well. Point being, it does allow you to deploy to the platform with just a one-liner. And I think probably right now is not the right time to debug whatever's going on. Maybe you could just then show what it looks like.
Okay.
So I would say, in general, the speed of rendering and on local issues, if we need to have massive the image so we can get it.
Only for the developer environment. So maybe this is really important. I want to go back to something we started the whole presentation with. Is there's 2 users at a minimum in almost every synthetic data pipeline. There's a computer vision user that wants the data, and there's a synthetic data engineer that's defining how the simulation should work. So what we're showing here is the environment that the synthetic data engineer works in before they deploy it to the cloud. That synthetic data engineer, their local compute is going to, yes, define, the resources that they have available for testing their local simulations. But once they deploy it to the cloud, then we have, full access to whatever's available in the cloud. And those are the resources that the computer vision user then gets access to when they start to ask for data at scale.
Yeah, that's correct, but still, when you keep the range of it's still going to be 10 10,000. But that rendering scheme depends on the container and the size of the.
No.
You would never do 10,000 images on your computer. So that's only for the developer. They would make one image usually, and that's usually what we're doing to see if the code works.
Okay.
And then deploy it to the cloud, and that's where you scale.
And it's different compute. It doesn't use your CPU when it's on the platform.
So rendering happens in massive on server.
Yeah,
That's right.
Yeah.
That was.
Yeah. I mean, I think, Dan showed there was a job running. And and you can kind of dig in here, and it showed all of the instances that are running. And that's on AWS, right? These are EC2 instances that we maintain. Yeah. So so what I did is so when you upload it, then I created a new channel, and because it was a new channel, I needed to make a new workspace or somehow associate that channel with the workspace. And I mean, you kind of just, and then here's what we get. So the preview ran, and most importantly, we can see that the render node now has this blur size, and you can go in and change the values and run different and do previews, and then come over to your, and then, all right, I'll slow down. So so I put this together and was like, I wonder how blurry it gets. And what do we, so, and why would we want to do blur in the first place? Is maybe the sensor was decayed from age or something, or decrepit, maybe from wind or from sun, or just maybe it's raining, and or for some reason there's a need for the model to get some training data for this kind of data that is modified because it needs like the blur effect is determined by the computer vision scientist as a good hypothesis to make an improvement on increasing the fidelity of the model. And so the data science engineer comes in and provides the blur option. And blur could be X and Y, or it could be spherical, like I've done here, just to make it equal in both directions. And so and then with the effect of it can be teased out by changing these values, maybe making it 5 or 10 or 2 or whatever. Like I could make one here that says 5, and then stage it or preview it if you want just one image. But if you want to get a better sense for what it might do, I would preview it, go to the jobs, and rename this staged graph, as blur size 5. And now I can kick off a run. Blur size 5. Give me 10 of them. And then you can see I've done this before, and you can, and these things, and they show up in the libraries, and you can take a look at how they're doing. Get a sense of of the impact.
Thank you.
So that's a day in the life of a synthetic data engine. Thank you.
All right, well, some of y'all have joined us for the whole journey. Certainly appreciate it. We've covered a lot of ground, like what the heck is synthetic data? Why do you care about it? What might you do if you're generating synthetic data? How do you run experiments? Think about quality. And then all the way into how you actually build out those pipelines from a granular standpoint and deploy them. It's a sophisticated environment, and there's a lot of stuff to cover. And I appreciate you guys for hanging out with us and learning
I
about it.
hear, we want to talk about some codes.
Yeah, sure. Let's if you are interested in playing around with some of this and you want to jump on the platform and just get started and generate some data, there's a few content codes up here. When you create your account, you can put those in. With your account, you'll get access to data sets, you have graphs, some analyses that have already been done in most cases. And so it's a great way to jump in and just have some fun with synthetic data. Ooh. Apparently that was Dear Sig V2 on the content. So yeah, feel free to try that out. And if you're interested in kind of furthering, going further down the journey of synthetic data, let us know. We're happy to help out. But anyway, really appreciate you guys spending the afternoon with us. Thank you. Do we know?
Oh, hang on.
Use it as a big, I think we probably use this balancing data set and real data set.
Oh, leave it up on the content codes. There's people taking.
Yeah, well, okay.
So you.
Which one? Do you want the links?
Oh, sorry.
You have.
Yeah, I see. Hold on. Oh, you're seeing this the whole
Yeah.
time?
You syndicate the balance.
Absolutely.
I forget that this is in
Right, like,
Zoom. And so it's like, oh, you're
I'll give you a
watching this the whole
specific
time.
in that phase one SBIR, right? We were looking at a data set where there were lots and lots of vehicles in there. They wanted to be able to detect cranes. There are very few cranes. They're difficult to label. And so we added a crane class. And what we were able to do was actually improve the AP scores on crane detection by a factor of 3 by adding synthetic data. Yeah, on a test on real data. Yeah.
And so, with commercially available hardware.
And then. Easier.
And I've looked at some.
Maybe for balancing. But then. The performance of classes, which.
So that's why I was looking
compared to the performance of other classes. Real good. Or at least you can see whenever a volume ratio.
I had to listen to
The performance is not as great as when you have the student.
Yeah, I think the reality is, if you have real labeled data, it's almost always going to match better, especially since your test set is almost always like that real data. So that's always going to match better. You have to really think carefully about your experiment if you want to really see synthetic data perform equally. So you'd have to pull data from a different domain or something like that. But in general, if you have data set that's ideally matched, then that's going to perform better than something that's not.
Why are we taking real
Real
images?
For some classes, that's.
Then.
That's right.
There's no other option.
In geospatial, so if that's what we find often works really well, is in geospatial specifically, there often is data, it's just not labeled.
That's kind of
So
like my thought.
if you
Yeah.
build
And
a pseudo
like you said,
label,
right now, there's
synthetic, run it on your real data, you can get a bunch of now real data with those, and you can start to unbind it that way.
People who hasn't talked to us yet,
Yeah.
I always,
No.
I assume that they assume that we need 10,000.
I haven't
So we can get into the details later.
But we do a lot of
But I mean,
national
it's hard
projects.
for me to-
Yeah, we have
Oh,
a
you only need
project
500
right now.
Right?
That's what
We
I
need
need.
some sort of
Because look,
something
like,
like,
I was talking to their friend,
for IR.
you know, it's a whole,
Because
what is
we
it?
can generate ER
Only
always
using, there's a lot of hype.
on the
Yeah.
engine, like, we have to-
Right, like, that's a, understand, but, you know, there's a lot of hype.
But the project is.
And it's like, is it, because you have like, you know, electricity was invented in the 19th century.
Sure.
Then on top of that, we had
But then when it comes
60-bit
to
transistors, then transistors enabled software.
we don't really.
And now, is this a transistor that we mentioned, you know, that we
Physics
talk
of
about virtual
IR,
networks?
different.
Or is it more or less?
Yeah.
It's not really actually.
Is it a pivot? Is it a curve?
It's far.
Like, what is it?
The way.
And
The
it's
distance
we're
you have
mathematically
between the
representing
syndicate, the real syndicate, the
7th
real
century,
IR,
17th
that's the distance
century.
you get.
Like, you know, gradient descent is just, you know,
So how
the
good
local
is it?
minimum of a probability density function.
We can show you
representing
examples.
that network, right?
And
So
we,
you need
oftentimes
that
what we do in an engagement is we would dig in and we'd say,
You know, we're looking
I-
at something
IR
like
is not
now
one
that's
term,
like,
right?
we're gonna
IR
have
is a lot of
we're gonna
different types of
design
systems,
humanity
types
out
of
of the
platforms, you know, we
equation.
talk about.
So you have that, and it's
I don't know about that, but I still that we need good quality data and a lot of.
WX and then
To get a good
MS,
representation.
from.
So how do I, if I run into any issue,
And what do you take?
and who do I talk to?
Westcam?
How does it all work? And which one of you guys is the guy that I would? Maybe get
we've-
those, take a picture of it.
Yeah, so you're taking, okay, you're taking aerial photography of it.
Yeah.
What we would typically do
Like,
in an
like, is there a
engagement,
presentation from
right,
online
is we would
software or-
first,
We will be sharing,
Right.
yeah.
we bring in our
Or
engineers.
just,
They would take down.
And I mean, if you
and then
go
we'd
into
show
the
you
platform,
examples, just a
like,
few examples, what it would.
I mean,
like
there's a
to look
question
like.
mark right here.
You mind if I take a picture of your,
Does that make sense? So we have a lot of experience with infrared. I'm not off the top of my head familiar with that sensor. I don't even know if
And then,
that's, you know, near infrared.
Yeah, and
midwave.
also like, so if you set up an
Midwave.
account.
We've done some midwave, the example that I showed with IR and
Yeah.
RGB.
You see
that was
that? But I mean,
midwave.
like,
You know,
like this goes right to our.
it's pretty good. I mean,
For
it's certainly, that is actually a blender
yeah,
based.
so
platform, the
like
one I
what I've
showed.
been doing is
But
I
it,
was.
but it takes
I was
into
working at
account
Microsoft
emissivity of all the surfaces and temperatures across all the surfaces.
in Windows
You end up with
Server and
some
cloud for a bunch of
Pretty
years.
realistic output.
Then
Yeah.
I met my wife, she's a doctor, and she's finishing off her thing, so then pandemic happened, and I just, I've always liked computer vision.
Oftentimes,
You know, and I started doing all this,
run
you
into
know,
those
pandemic, right,
circumstances.
right,
Yeah,
you know, and then something,
Dreaming.
yeah, so I
We
built a
can help
computer,
build something
I started
out
putting
and
nice
deploy
graphics,
it.
RTX 3090,
But we don't actually
fine,
get, like,
one of
your
those.
engineer
Started going, playing around, started going through all the pseudo libraries and getting into it, and I go, oh, wow, instead of advising other startups and doing what I do, let me see if I can find, like, the biggest problem was the sheer number of, amount of data you need to train these models. And then I started looking at the synthetic data.
That's why you're doing the YOLO thing. right? 'Cause it's
Yeah, yeah,
faster.
YOLO's faster, and then I.
Well, YOLO is like also for like just snapshot. I mean, it's like anything it can operate like 100 hertz.
Right, right, there you go, right,
Yeah.
and then what it is, I looked at, well, YOLO, and then, you know, there's all these Python, I wrote a little Python app, or not Python app, a little Python program, and I saw some Google libraries to go into YouTube, because I need to look at video, right, like to see there on how am I optimizing my models, when I'm looking at, so then any YouTube video I can look at, and then, and then I started playing around with LiDAR, there's some LiDAR videos out there.
That's right.
The same object
We can help with
represented
both.
LiDAR versus represented